radio signal leaves Earth and travels for nearly a full day before it reaches Voyager 1. There is no road beneath it, no atmosphere around it, and no landmark waiting at the far end. The command moves outward at the speed of light, crossing the orbits of the planets, passing far beyond Pluto, and continuing into the region out of the Sun's protective heliosphere. Only then does it arrive at a machine launched in September of 1977. Voyager 1 is still there. Its dish remains aimed toward the distant point where Earth can be found. Its computers still carry out instructions written for hardware from another era. Two science instruments continue to measure plasma waves and magnetic fields in a region no other operating spacecraft has reached. Nearly 49 years after launch, the mission has become less like a planned expedition and more like a long conversation maintained across a widening distance. The cold is part of that story, though not in the way it is often imagined. Space does not seize a spacecraft and freeze it in an instant. There is almost no matter around Voyager 1 to conduct heat away and no moving air to carry warmth from its surfaces. In vacuum, the spacecraft loses energy mainly by radiating it. The process is steady, and it becomes slower as the spacecraft cools. That does not make survival automatic. Electronics still need workable temperatures. Propellant lines cannot be allowed to fall beyond safe limits. Instruments, sensors, computers, and radio systems all depend on a shrinking supply of electricity. Every watt used to warm one component is a watt unavailable to operate another. Every system kept alive adds pressure to a power source that has been fading since the day of launch, and yet the spacecraft has never depended on sunlight. Voyager 1 carries 3 radioisotope thermoelectric generators. Inside them, plutonium-238 releases heat as its atoms decay. Thermocouples convert a small portion of that heat directly into electrical power, without turbines, pistons, or circulating fluids. At launch, the 3 generators produced roughly 470 watts together. Year by year, their output has declined, and the mission team has answered by switching off heaters, instruments, and other equipment in a carefully chosen order. This is not a story of a machine defeating the laws of physics. It is a story of engineers working within them. The same radioactive decay that limits Voyager's future has sustained its long life. The same vacuum that leaves it exposed to deep space radiation also prevents rapid convective cooling. The same enormous distance that weakens its radio signal gives it access to measurements that cannot be collected near Earth. Nothing about its survival comes from a single miraculous component. It comes from a chain of decisions. Insulation wrapped around the spacecraft body, redundant systems waiting through decades of disuse, power budgets revised 1 watt at a time, commands tested on Earth before beginning their day-long crossing, and a narrow radio beam held toward a planet that has become almost indistinguishable from the stars around it. Tonight, the journey follows that chain. It begins with heat released inside a decaying isotope. It moves through metal junctions, insulated compartments, aging computers, fuel lines, antennas, and ground stations. And along the way, it reveals how a spacecraft built for encounters with Jupiter and Saturn became the longest-running experiment in keeping a human-made machine alive between the stars. Far beyond the familiar planets, Voyager 1 continues to spend its remaining power with care. There is another layer here, one that begins with a familiar word, and then asks us to set familiar experience aside. Cold. On Earth, cold usually arrives through contact. Winter air moves across your skin, water draws heat from your hand. A metal railing feels colder than wood because it carries energy away more efficiently. In each case, matter is involved. Molecules collide, mix, and transport heat from one place to another. Voyager 1 does not live in that kind of environment. The space around it contains particles, but they are spread so thinly that they cannot cool the spacecraft the way air cools an object on Earth. There is no wind moving across its body. There is no surrounding gas dense enough to absorb much of its warmth. Even the phrase temperature of space can become misleading, because different parts of the environment can be classified by different temperatures, without behaving like a room, an ocean, or a winter night. The individual particles of the interstellar medium can carry considerable energy. Scientists may describe that sparse gas as thousands of degrees above absolute zero. Yet there are so few atoms in any given volume that their total ability to warm or cool a spacecraft is very small. A single fast-moving particle may be energetic, but a near-empty region does not deliver many collisions. Radiation matters far more. Every object with a temperature above absolute zero emits electromagnetic energy. A warm spacecraft releases much of that energy as infrared radiation. The process requires no air and no physical contact. Photons leave the surface and carry energy away into space. This is how Voyager cools. It is also why the spacecraft does not freeze all at once. As an object becomes colder, it radiates less power. Cooling slows as the temperature falls, moving toward a balance between the energy being lost and the energy still being supplied. For Voyager, that supply comes from several places. The 3 radioisotope generators release heat continuously as plutonium-238 decays. Only a fraction of that heat becomes electricity. The rest remains thermal energy and is radiated away from the generator housings. The generators are mounted away from the main body, partly because they are hot, and partly because their radiation and magnetic effects could disturb sensitive instruments. Inside the central body, electrical power becomes heat again. A computer processing a command warms slightly. A radio circuit carrying current warms slightly. Instruments, power converters, and cabling all release heat while operating. In a house, that waste heat may be unwanted. On a spacecraft traveling far beyond the planets, it becomes part of the thermal design. Voyager's interior is therefore not warmed by one hidden furnace. It is sustained by a distributed flow of energy. Radioactive decay creates heat. Thermocouples turn some of it into electricity. The electrical systems use that power, and much of it eventually returns to heat within the spacecraft. Insulation slows the escape of that energy long enough for important components to remain within workable limits. The insulation is made from many thin reflective layers separated so that very little heat can pass directly from one layer to the next. From a distance, these blankets may look delicate, almost like metallic wrapping. Their purpose is precise. Each reflective surface sends part of the outgoing infrared energy back inward. With many layers, the rate of heat loss becomes much smaller than it would be from an exposed metal structure. The blankets do not create warmth. They preserve it. That distinction shaped the spacecraft from the beginning. Engineers could not stop the generators from weakening, and they could not surround Voyager with a permanent atmosphere. What they could do was control the pathways through which energy moved. They could place hot components away from sensitive ones. They could conduct heat toward areas that needed it. They could isolate exposed structures. They could add electric heaters where passive insulation was not enough. The result was not one uniform temperature. Voyager is a collection of thermal neighborhoods. The equipment bay, the external instruments, the propellant tanks, the lines leading to the thrusters, and the long booms extending into space do not all gain and lose heat at the same rate. A component shaded by the spacecraft body experiences a different balance from one facing open space. A circuit that operates continuously warms itself more than a sensor that waits between measurements. This unevenness becomes more important as power declines. When the spacecraft was young, there was enough electricity to run many instruments and heaters at once. Their operation produced additional warmth, as systems were turned off. The power savings helped extend the mission, but the lost electrical activity also removed heat from the places those systems once occupied. Saving power could make the spacecraft colder. That is one of the subtler problems the mission team has faced. A heater may consume electricity, but an instrument also warms its surroundings while it runs. Turning either one off changes the entire thermal pattern. The team cannot treat the power budget and the temperature budget as separate ledgers. They are two descriptions of the same diminishing resource. Sunlight still reaches Voyager, though it has become faint, more than 100 times farther from the Sun than Earth. The spacecraft receives less than 1/10,000th of the solar energy that falls near our planet. The Sun remains useful as a reference point for orientation, but it provides very little warmth compared with the conditions of the inner solar system. Beyond the spacecraft, the sky offers almost no help. Starlight arrives from every direction, but not in quantities that can maintain its systems. The cosmic microwave background fills space with radiation left from the early universe, yet it represents a temperature of only about 2.7 Kelvin. It establishes a deep thermal background, not a sudden force pulling Voyager toward complete stillness. The spacecraft survives in the difference between those scales. Outside, energy arrives sparingly. Inside, atoms continue to decay, circuits continue to work, and reflective layers continue to delay the departure of heat. The balance is fragile, but it is understandable. Voyager remains active, not because the cold has failed to reach it, but because its designers gave every remaining watt a path, a purpose, and time. At the center of Voyager's long survival is as a source of energy that does not burn, spin, circulate, or wait for sunlight. It begins inside the nuclei of atoms. Voyager 1 carries 3 radioisotope thermoelectric generators mounted on a boom away from the main body of the spacecraft. They appear as dark cylindrical units, arranged beyond the equipment bay, separated from sensitive instruments, and positioned where their heat can radiate into space. Their name describes the entire process. Radioisotope refers to the unstable atomic material releasing energy through radioactive decay. Thermoelectric refers to the conversion of heat into electricity. Generator describes the final purpose, supplying power to the spacecraft. There are no moving parts inside these generators. No turbine turns, no piston rises, no fuel line feeds a flame. The system depends on a difference in temperature and on a physical effect that was known more than a century before Voyager left Earth. In the early 19th century, Thomas Johann Seebeck observed that a voltage could appear when 2 different conducting materials were joined, and their junctions were held at different temperatures, one side warm, the other side cooler. The temperature difference encouraged electric charge to move through the circuit. This became known as the Seebeck effect. Inside Voyager's generators, radioactive material provides the warm side. The surfaces exposed to space help maintain the cooler side. Thermocouples placed between them convert part of that temperature difference into electrical energy. The conversion is not highly efficient. Most of the heat does not become electricity. It leaves the generator as thermal radiation. But efficiency was not the only requirement for Voyager. Reliability mattered more. A spacecraft traveling beyond Jupiter could not depend on solar panels in the same way a vehicle near Earth might. Sunlight weakens with the square of the distance. Twice as far from the Sun, a spacecraft receives 1/4 as much solar energy. 10 times farther away, it receives 1/100th. By the time Voyager passed the outer planets, sunlight had become too weak for the compact solar technology available during the mission's design. Large panels would have added mass, complexity, and new mechanical risks. They would also have needed to remain oriented toward a sun, that was becoming less useful with every outward mile. A radioisotope generator offered something different. Its power source traveled with the spacecraft. It did not depend on illumination, seasons, shadows, or the position of a planet. It could operate while Voyager crossed Jupiter's dark magnetosphere, passed behind Saturn, and continued into regions where the sun looked more like a brilliant star than a nearby source of warmth. The isotope chosen for this work was plutonium-238. Plutonium has several isotopes, and their behavior differs according to the number of neutrons inside each nucleus. Plutonium-38 is not the isotope usually associated with nuclear weapons. It is valued for spacecraft power because it releases heat steadily through alpha decay. During that decay, a plutonium-238 nucleus emits an alpha particle made of 2 protons and 2 neutrons. The remaining nucleus becomes uranium-234. A small amount of mass is converted into energy, and within the fuel material, that energy becomes heat. The process continues without commands from Earth. It does not need to be started each morning or adjusted to match the spacecraft's schedule. Quantum probability governs which nuclei decay at any particular moment, but across a large quantity of material, the overall heat output follows a stable and predictable curve. That predictability allowed engineers to plan decades ahead. Plutonium-238 has a half-life of about 87.7 years. After that span, half of the original nuclei remain undecayed. The material does not suddenly stop producing heat at the end of one half-life. Its output declines gradually following an exponential curve. The length of the half-life is part of what makes the isotope useful. An isotope that decayed much faster could release intense heat at first, then weaken too quickly for a long mission. One that decayed far more slowly might remain active for centuries, but produce too little heat per unit of mass. Plutonium-238 occupies a useful middle ground. It releases enough energy to power a spacecraft while declining slowly enough to remain valuable across many decades. When Voyager 1 launched, its 3 generators produced about 470 watts of electrical power. That was modest, even by household standards. A kitchen appliance can consume more. A modern desktop computer may use a meaningful fraction of it. Yet the spacecraft was never designed like a household or an office. Every circuit had a defined purpose. Every instrument operated within a carefully measured budget. Systems were selected not only for what they could do, but for how little energy they required while doing it. The mission began with enough electrical margin to operate cameras, spectrometers, particle detectors, computers, heaters, transmitters, and attitude control equipment. It was still a limited supply, but in the early years the spacecraft could support the work of a planetary explorer. Jupiter and Saturn demanded cameras. Their atmospheres, rings and moons could be studied through reflected sunlight. Imaging systems captured changing clouds, volcanic plumes, fractured ice, narrow ringlets, and the orange haze surrounding Titan. Other instruments measured radiation, magnetic fields, particles, and atmospheric composition. After Saturn, the mission changed. There were no more close planetary encounters ahead for Voyager 1. Its cameras would eventually have little to photograph. The spacecraft was leaving the realm of large nearby worlds and entering a region where particles and fields mattered more than visible surfaces. Power management began to follow that transition. Some instruments were no longer needed. Others became less useful as the spacecraft moved away from the planets they had been built to study. Systems were turned off, one by one, not because they had all failed, but because the electricity they consumed had become more valuable elsewhere. This is one of the reasons Voyager's long life cannot be credited to the generators alone. The plutonium provided declining power. The mission team decided how to spend it. As radioactive decay reduced the heat supply, the thermocouples also aged. Their materials had been exposed to decades of heat, radiation, and repeated thermal stress. The difference? In temperature still produced electricity, but the conversion became less effective over time. The power decline, therefore, came from two processes at once. There was less heat available as plutonium decayed, and a smaller fraction of that heat became useful electricity as the thermoelectric materials degraded. Neither process could be repaired. No command from Earth could restore the original fuel. No technician could replace a worn thermocouple. The mission team could only respond to what remained by reducing demand. A heater might be switched off. An instrument might be placed into permanent silence. A backup system might be preserved until another component showed signs of wear. Each decision extended one part of the mission by surrendering another. This sounds severe, but it was built into the logic of Voyager from the beginning. The spacecraft was not expected to retain every ability forever. Its design allowed systems to be isolated. Redundant paths allowed commands and data to move around certain failures. Instruments could be powered separately. Heaters could be managed according to changing conditions. The spacecraft could become simpler without immediately becoming useless. Over the years, Voyager gradually changed from a fully equipped planetary observatory into a smaller scientific presence. Its cameras went dark. Spectrometers stopped collecting data. Other instruments ended their work as power became scarce. What remained was chosen for the environment ahead. In interstellar space, the most valuable measurements come from magnetic fields, charged particles, and plasma waves. These do not require a nearby planet or a bright landscape. They require the spacecraft to remain oriented, powered, and able to transmit. That final requirement consumes a large share of what the generators still provide. Voyager's radio must prepare information for transmission, amplify the signal, and send it through the high-gain antenna toward Earth. Computers must continue organizing science and engineering data. Attitude control systems must keep the dish aligned. Selected heaters must protect components whose failure would end communication. The surviving mission is therefore a narrow chain. Radioactive decay creates heat. Thermocouples create electricity. Electricity powers the computers and radio. The attitude system holds the antenna toward Earth. Ground stations listen for the returning signal. Break any critical link and the conversation may end. For almost half a century, that chain has held. The people who first assembled the generators could calculate the half-life of the fuel and estimate the decline of the thermocouples. They could model temperatures and assign power reserves. What they could not fully know was how long the spacecraft around those generators would remain responsive. They could not know which electronic components would survive radiation for decades. They could not know whether dormant thrusters would awaken after years without use. They could not know whether future engineers would still understand the commands, memory maps, and electrical pathways of a machine designed before many of them were born. The generators made the long mission possible, but human continuity has helped turn possibility into history. Across generations, teams have inherited the same shrinking supply of watts. Each group has studied records left by the one before it. They have learned which temperatures matter most, which systems can tolerate risk, and which changes cannot be reversed. The plutonium continues its transformation without awareness of any of this. Atom by atom, it becomes something else. Heat emerges, electricity follows. A signal forms and begins its outward journey from the antenna. The source grows weaker, but it has not yet gone dark. There is a moment in the life of an aging spacecraft when saving electricity is no longer a simple act of subtraction. Turning something off may free power, but it also removes heat. A circuit that once consumed a few watts may have warmed a neighboring cable. An instrument that no longer serves the mission may still have kept part of the spacecraft above a critical temperature. When that instrument falls silent, the electrical budget improves while the thermal balance changes. Voyager 1 has been living inside that trade for decades. Its body was designed as a connected thermal system. Equipment boxes share structure. Wiring harnesses pass through insulated compartments. Conductive paths move heat through metal. Reflective blankets slow radiation from exposed surfaces. Small electric heaters protect components that cannot rely on nearby electronics for warmth. When power was plentiful, several of those heaters could operate without threatening the mission. As the radioisotope generators weakened, the team began switching off the ones judged least necessary. Each change was studied in advance, but the spacecraft was entering conditions no original mission plan had described. Engineers had to learn how its temperatures responded, not over days, but over years. The colder spacecraft did not become inactive. It became less forgiving. Some electronic components can tolerate temperatures below their original operating range. Others cannot. Lubricants may thicken. Materials contract by slightly different amounts. Electrical resistance shifts. Connections that have remained stable for decades can become more vulnerable as thermal margins narrow. The propulsion system is especially important because Voyager must keep its high-gain antenna aimed toward Earth. The spacecraft is not flying through air, so it does not need a rudder or wings. It maintains orientation with small hydrazine thrusters. Each firing lasts only a fraction of a second. The resulting puff of gas gives the spacecraft a tiny rotational push, correcting the gradual movement that would otherwise carry the antenna away from its target. These corrections are small, but they are not optional. Voyager's radio beam is narrow. Earth, seen from the spacecraft, lies close to the sun in the sky and occupies no meaningful width to the unaided eye. The antenna must be held within a limited pointing range so that commands can arrive and telemetry can return. If orientation is lost beyond the spacecraft's ability to recover, the probe could remain electrically alive while becoming unreachable. Hydrazine is well suited to this work. It can be stored for long periods and does not need a separate oxidizer inside Voyager's small thrusters. When the liquid reaches a catalyst bed, it decomposes rapidly into hot gases. Those gases leave through a nozzle and produce thrust, but the fuel system has aged along with everything around it. Voyager carries several branches of thrusters. Two were intended mainly for attitude control, while another was used for trajectory corrections during the planetary phase of the mission. Once the spacecraft settled onto its long outward path, the distinctions became less important. Different branches could be used to maintain the antenna's orientation. That flexibility became one of the spacecraft's remaining forms of resilience. Over many years, narrow tubes inside the thrusters began to clog. The material responsible was silicon dioxide, formed as a byproduct of aging components in the fuel system. The openings directing hydrazine toward the catalyst beds became progressively narrower. A thruster could still operate, but it had to fire more often or work less efficiently to create the needed correction. The team responded by moving from one branch to another. A set that had accumulated less use could take over from a set showing more severe restriction. This did not repair the clogged branch. It distributed wear and preserved alternatives. In a younger spacecraft, such a change might have been routine. On Voyager, it required a thermal plan. Some of the unused thrusters had become cold after their heaters were turned off to conserve electricity. Activating them without warming them first could damage the hardware. The solution seemed direct: turn the heaters back on. The difficulty was that Voyager no longer had spare power waiting to be assigned. By 2024, Nearly everything still drawing electricity was considered necessary. The radio, computers, attitude control system, and remaining scientific instruments all had reasons to stay active. Turning on dormant thruster heaters meant another load had to be removed, even if only briefly. The team considered switching off a science instrument for a short time. They rejected the idea because an old instrument that powers down may not start again. A temporary shutdown could become permanent. Instead, engineers found another path. They calculated that one of the spacecraft's main heaters could be turned off for less than an hour. That would release enough electrical power to warm the colder thruster branch. The interval had to be long enough for the dormant hardware to reach a safe condition, but short enough to keep the rest of the spacecraft within its thermal limits. The commands were prepared and tested on Earth. Then they were transmitted across interstellar distance, carrying instructions for one heater to fall silent while another awakened. The spacecraft executed the sequence on its own. On August 27, 2024, the team confirmed that the selected thrusters were operating and helping to point Voyager toward Earth. Nothing about the maneuver changed the amount of plutonium on board. No new energy was added. Power was moved through time and space, taken briefly from one thermal need and directed toward another. The success came from understanding how long each part of the spacecraft could tolerate a different condition. This is what survival looks like near the end of a power budget. It is not simply keeping every system warm. That would consume too much electricity. It is deciding which component needs heat now, which one can cool for a while, and which one may never be turned on again. A similar problem appeared in the spacecraft's roll control system. Voyager must control rotation around the line running through its high-gain antenna. Without that control, the spacecraft could slowly roll, affecting instruments, sensors, and communication. A primary set of roll thrusters had been considered unavailable since 2000 after their heaters stopped working. Backup thrusters carried the responsibility for years. By 2025, those backups were also facing the effects of age and clogging. Engineers revisited the older failure. They suspected the original heaters might not have been physically destroyed. A disturbance in the power control circuitry may have left a switch in the wrong state. If the circuit could be returned to its intended configuration, the heaters might function again and make the older thrusters available as another reserve. The attempt carried risk. If the spacecraft's star tracker drifted too far from its guide star, while the dormant thrusters were enabled, Voyager's automatic programming could command them to fire. Cold thrusters firing before their heaters worked could be damaged. The team had to align the spacecraft carefully, activate the system, and restore heater power in the correct order. They also had to work within the rhythm imposed by distance. A command sent from Earth required more than 23 hours to reach Voyager 1. News of the result required more than 23 hours to return. The people watching the telemetry could not intervene in real time. By the moment they saw a temperature begin to rise, the event itself had already happened almost a day earlier. On March 20th, 2025, the returned data showed that the heaters had warmed. Thrusters once treated as lost were available again. The recovery did not make Voyager young. It restored one option, one more layer of redundancy inside a system with fewer choices each year. That option mattered because a large deep space network antenna in Australia was about to enter a long period of upgrades. Communication opportunities would become more restricted, and the team wanted the spacecraft prepared before that change. The calculations behind these choices are never based on a single thermometer. Temperatures are inferred from sensors placed at selected points, from the known flow of electricity, and from models describing how heat moves through structures built in the 1970s. Some locations cannot be measured directly. Engineers must estimate them from nearby readings and from the way the spacecraft responded to earlier changes. That makes every heater decision partly an act of reconstruction. The team studies records from previous decades, compares predictions with telemetry, and adjusts the model when the old spacecraft behaves differently from expectation. A blanket may retain heat better than anticipated. A powered cable may warm a nearby assembly. A component may continue operating below the range once considered safe. These are not invitations to become careless. They are new boundaries learned from the only Voyager, one that exists. From Earth, the process unfolded through screens, memory maps, thermal models, and lines of telemetry. There was no view of the spacecraft warming. No camera watched frost retreat from a fuel line, and in the near vacuum, there would have been no familiar frost to see. The evidence arrived as numbers: heater current, component temperature, thruster response, antenna pointing. You might be resting now in a room where warmth seems almost passive. Walls hold it, air circulates it. A thermostat corrects small changes without asking for attention. Voyager has no such abundance. Its heat is counted in watts that cannot be replaced. Its insulation has no maintenance. Its heaters depend on a generator losing capacity every year. Even the act of keeping one thruster ready may require another part of the spacecraft to accept a temporary chill. The machine survives because it does not need to be warm everywhere. It needs the right places to remain warm enough, at the right moments for the next command and the next correction. Its thermal design allows heat to be rationed. Its redundant branches allow wear to be redirected. Its software can carry out sequences while Earth waits for the answer. Far from the sun, longevity has become an art of controlled imbalance. One heater rests so another can work. One thruster branch waits while another keeps the antenna aligned. One instrument ends its service so a smaller set can continue measuring the space between stars. The spacecraft does not preserve its original form of life. It survives by becoming less carefully. The next surviving path begins at the center of Voyager's body and ends inside a radio telescope on Earth. Between those 2 points lies a distance so large that ordinary ideas of communication begin to fall away. Voyager 1 carries no cable home. It has no nearby relay station and no second spacecraft waiting between worlds to pass its message inward. Every piece of engineering data, every measurement of magnetic fields, and every command acknowledgement must cross the full distance directly. The spacecraft does this with radio. Its high-gain antenna is the most recognizable part of its structure, a broad parabolic dish facing back toward the inner solar system. The dish is about 3.7 meters across. Its curved surface gathers incoming radio waves and concentrates them toward a receiver. When Voyager transmits, the same geometry helps direct energy into a narrow beam, rather than allowing it to spread evenly in every direction. Narrow does not mean easy. Even a carefully focused beam becomes wider as it travels. By the time Voyager's signal reaches Earth, the energy has been spread across an area far larger than the planet. Only a minute fraction falls on any receiving antenna. The spacecraft's transmitter is not powerful by household standards. It sends radio energy with a power measured in only a few tens of watts. That signal begins clearly at the spacecraft, then weakens with distance according to a simple rule. As the expanding wave covers more area, the available energy per unit area falls with the square of the distance. Double the distance, and the received intensity falls to 1/4. 10 times the distance leaves 1/100th. Voyager has spent decades moving farther away, so the challenge has never stopped increasing. The transmitter has aged. The available electrical power has declined. The signal has had to cross a growing span of space while remaining recognizable. at the far end. This is where the deep space network becomes part of the spacecraft. The network is distributed around Earth at 3 main complexes, one in California, one near Madrid, and one near Canberra. Their positions allow the planet's rotation to carry a distant spacecraft from the view of one site into the view of another. Voyager does not remain above a single horizon all day, so communication becomes a relay performed by the turning Earth. The largest antennas are immense compared with the dish aboard Voyager. Their size gives them collecting area. A larger dish intercepts more of the faint radio energy reaching Earth and directs it towards sensitive electronics. The receivers are cooled and shielded, so their own internal noise does not overwhelm the signal. The sky itself is not radio silent. Charged particles, distant stars, galaxies, and human technology all contribute noise. Earth's atmosphere and electrical systems add their own interference. The receiving equipment does not simply hear Voyager in an empty band. It searches for a known pattern at a known frequency, arriving from a known direction and changing in predictable ways as Earth and the spacecraft move. Knowing where to listen is part of what makes listening possible. Engineers calculate these spacecraft's motion and Earth's rotation. They account for the relative velocity between transmitter and receiver, because that motion shifts the apparent frequency through the Doppler effect. They know how Voyager's carrier signal should behave and how its data are encoded. Signal processing can then combine weak evidence over time until a coherent message emerges from the background. The received power is so small that everyday comparisons begin to lose meaning. What matters is not whether the signal feels strong. It is whether the receiver can distinguish its ordered pattern from random fluctuations. Voyager's radio transmission is coherent. Its frequency and modulation follow rules. Noise does not follow those same rules for long. By integrating the signal and applying error correction methods, the ground system can recover information that would otherwise seem absent. The process favors patience. A larger amount of data requires more radio time. A lower data rate allows each bit to receive more of the transmitter's limited energy and gives the ground system more opportunity to identify it. As Voyager moved outward, its transmission rates were reduced. The spacecraft now sends information at a pace that would feel almost motionless beside a modern internet connection, but the comparison is misleading. Voyager sends from interstellar space using a generator that has been fading since the 1970s. The achievement is not the number of bits arriving each second. It is that any reliable bits arrive at all. Those bits carry several different kinds of meaning. Some describe the health of the spacecraft. Temperatures, currents, voltages, thruster activity, computer states, and instrument conditions are arranged into engineering telemetry. Other bits carry measurements of the environment through which Voyager moves. Together, they allow people on Earth to know both what the spacecraft is sensing and whether it remains capable of sensing it. Before transmission, onboard computers must collect and format the information. That step cannot be skipped. Raw electrical outputs from instruments are not naturally organized into a radio message. They must be sampled, converted into digital values, placed into frames, labeled, and passed to the communications system in the correct sequence. The radio then modulates the carrier signal, changing selected properties of the wave so that the data ride within it. At Earth, the process runs in reverse. The antenna gathers the faint carrier. Receivers isolate the appropriate band. Computers detect the modulation, reconstruct the bit stream, correct recoverable errors, and separate engineering information from science data. A measurement made beyond the heliosphere becomes a row of numbers. On a screen, the transformation may seem plain, but every stage depends on the one before it. An instrument can be healthy while its data formatter fails. A computer can format data correctly while the transmitter sends at the wrong frequency. The radio can operate while the antenna points slightly away from Earth. A perfect signal can leave Voyager and still be lost if no ground antenna is scheduled to receive it. Communication is not one device. It is a chain extending from a sensor in interstellar space to a person interpreting the result on Earth. The chain also works in the opposite direction. Commands begin as carefully prepared instructions. Engineers test them against models and ground-based systems, looking for unintended interactions. They convert the sequence into the format Voyager's computers understand and schedule a deep space network antenna to transmit it. Then the command leaves Earth. For more than 20 hours, nothing can be changed. The signal is already traveling, and the spacecraft has not yet received it. Once it arrives, Voyager carries out the instruction according to its stored programming. The response begins another journey of more than 20 hours. A single exchange, therefore, unfolds across nearly 2 days. There is no conversation in the ordinary sense. No one asks a question and watches the machine answer a moment later. Mission Control acts, then waits through a span longer than a full waking day before knowing whether the first part of the exchange even reached its destination. This delay shapes every recovery. Commands must be complete enough for Voyager to act safely. Without supervision, sequences need fallback behavior. Engineers must anticipate what the spacecraft might do if a sensor reports an unexpected value, or if a computer enters a different state from the one predicted. By the time the answer returns, Voyager has already lived with the consequences for many hours. That distance creates a peculiar form of responsibility. The people caring for the spacecraft cannot touch it, watch it directly, or intervene during the moment of change. They must understand it well enough to prepare the action in advance. The antenna's pointing makes that responsibility even sharper. Voyager rotates slightly under the influence of small mechanical effects and the motion of its own systems. The attitude control thrusters correct those changes. Sun sensors and a star tracker provide references. The spacecraft keeps the dish aimed toward the place where Earth will be, not merely where it appeared when the command began. The beam must cross a moving geometry. Earth travels around the Sun. Voyager continues outward. The planet rotates beneath the receiving stations. The radio frequency shifts slightly as the distance changes. Each element is predictable, but none is fixed. Across human history, distant lights were used to guide travelers toward home. Stars above oceans helped navigators preserve direction when no land was visible. Their positions were learned through repetition and carried from one generation to the next. Voyager reverses that old relationship. It uses the Sun and a bright star to preserve its own orientation, while people on Earth use radio telescopes to follow an object too faint to see. The guide is now the traveler, and the home it points toward is a planet hidden within the glare of a distant star. The connection remains possible because both ends continue to cooperate. Voyager conserves power, formats its data, holds its attitude, and transmits through the same dish it carried past Jupiter. Earth supplies antennas far larger than anything the spacecraft could have lifted. Receivers improved across decades, updated software, orbital calculations, and people who remember how to speak to a computer built in another technological age. The spacecraft did not carry the entire communication system with it. Part of Voyager has always remained here. As ground equipment improved, the mission gained abilities that were not present at launch. Better receivers could detect weaker signals. More capable processing could extract information more effectively. Antennas could be combined for difficult observations. The aging spacecraft continued using its original hardware, while Earth became a more attentive listener. This is one of the hidden reasons the mission endured. Voyager survived, not only because it was built with care, but because the world behind it kept building the means to hear it. There may be long stretches when no science result sounds dramatic. The signal may contain only a small change in magnetic field strength, a plasma oscillation, a component temperature, or confirmation that a heater responded. Yet each packet has crossed the space between stars and arrived through a path held together by timing, geometry, and very small amounts of energy. The radio link is fragile, but it is not accidental. It is renewed with every pointing correction, every scheduled antenna pass, every frequency calculation, and every successful decoding. The conversation continues because thousands of details remain aligned at once. Somewhere beyond the heliosphere, the dish faces home. On Earth, another dish turns toward the same narrow line in the sky. Between them, the signal keeps finding its way. In November of 2023, Voyager 1 did not disappear. The carrier signal still reached Earth. Engineers could see that the spacecraft was receiving commands and that its radio remained active. But the information riding on that signal had lost its structure. Science's measurements and engineering telemetry arrived as repeating patterns that could not be interpreted. The voice was present, but the words were gone. That distinction mattered. A silent transmitter would have pointed toward one set of failures. A misaligned antenna, a loss of electrical power, or a problem in the radio system might have ended contact completely. Instead, Voyager continued sending energy toward Earth. Something inside the chain that prepared its data had stopped working correctly. The investigation turned toward the flight data subsystem. Voyager carries 3 interconnected computers, each designed for a different part of the mission. The command computer receives instructions and manages broad spacecraft functions. The attitude and articulation control system keeps the antenna oriented and once directed movable instruments during the planetary encounters. The flight data subsystem gathers measurements, organizes them, and prepares the stream that the radio sends home. By modern standards, these machines are small and unfamiliar. They were created during an era when memory was measured in kilobytes. Software was written close to the level of the hardware, and every instruction had to justify the electricity and storage it consumed. There is no general purpose operating system aboard Voyager waiting to hide the details. Its programs are closely tied to the physical arrangement of memory, processors, instruments, and communication circuits. That old architecture is one reason the spacecraft uses so little power. It is also why repairing it requires a kind of patience rarely demanded by present-day computing. The engineers cannot replace a module, connect a diagnostic cable, or restart the spacecraft from a clean copy stored in a distant data center. They must infer the condition of hardware launched before many members of the current team were born. At first, the unreadable pattern offered only limited clues. Every attempt to learn more required a command to travel outward and a response to travel back. A single diagnostic step could occupy almost 2 days. If the returned data did not answer the question, another command had to be prepared, checked, transmitted, and followed through another long interval. The team worked gradually. They asked the spacecraft to change the way it operated. They compared the resulting signals. They searched old documents for descriptions of memory addresses and software routines. They examined records created by engineers who had designed the system in the 1970s. The mission had become an act of technical archaeology. The hardware was far away, but the knowledge needed to reach. It was also distant in another sense. Original drawings had been preserved in older formats. Code had been written for a processor, unlike those used in current computers. Some details lived in notes made during tests performed decades earlier. Documentation became a surviving component of the spacecraft. Without it, the metal and electronics beyond the heliosphere might still have been functioning, but no one on Earth would have known how to guide them around the failure. The continuity of the mission depended on paper records, archived software, institutional memory, and people willing to learn an obsolete system with the same care once used to build it. By March of 2024, a diagnostic response revealed a more complete pattern from the flight data subsystems memory. Engineers compared that return with the expected software. One region did not match. A single memory chip appeared to have failed, taking with it part of the code required to package science and engineering information. The exact cause could not be known. An energetic particle may have damaged the chip. Age may have done what age eventually does to electronic material. Voyager had crossed intense radiation regions near Jupiter, spent decades exposed to cosmic rays, and operated far beyond its planned lifetime. A component surviving for 46 years had already exceeded any ordinary expectation placed upon it. The failed chip could not be restored, but the code it once held was not lost on Earth. The team knew what instructions belonged there. The question was whether those instructions could be placed somewhere else, inside the flight data subsystem. There was no single empty region large enough to contain them. Voyager's memory had been allocated carefully long ago. The remaining working areas held other instructions and data. Engineers therefore divided the missing code into smaller sections and placed those sections in separate locations. Moving software in such a tightly connected computer changes more than its address. Other routines need to know where to find it. References embedded elsewhere in the program must be altered. The pieces must still execute in the correct order. A change that looks small on a memory map can affect the path followed by many later instructions. The repair was closer to rearranging rooms in a house without moving the doors. Each doorway had to lead to the new location. Every route through the building had to remain usable, and the work had to be performed through a radio connection that allowed no immediate correction if a mistake appeared. The team began with the software responsible for returning engineering telemetry. That choice was practical. Before science could resume, engineers needed readable information about the health of the spacecraft. Temperatures, voltages, currents, and computer states would show whether the new arrangement was working and whether later changes could be attempted safely. The commands were tested on Earth before transmission. Ground systems modeled the behavior of the old computer. Engineers reviewed the sequence repeatedly, checking that the relocated code would fit, that references would point to the proper addresses, and that no necessary memory would be overwritten. Then the instructions left Earth. For nearly a day, the repair existed only as a radio wave crossing the outer solar system. It passed the orbit of Neptune and continued through the heliosphere, then beyond its boundary toward the small dish held on Voyager's body. The spacecraft received the command and rewrote part of its own memory. Another day later, the answer reached Earth. On April 20th, readable engineering telemetry returned for the first time in more than 5 months. The data were not merely proof that the transmitter still worked. They showed that the flight data subsystem could once again assemble a meaningful message. The repair continued in stages. Additional portions of the missing software were relocated. Science data pathways were restored. By June, the operating instruments were again returning usable measurements of interstellar space. The recovery did not remove the failed chip. That damaged region remained unusable. Voyager survived by changing the route through what was left, much as its power system survives by moving electricity away from equipment that had ended its work. In both cases, the spacecraft continues through redistribution rather than renewal. There is a pattern in these late years. A thruster clogs and another branch takes over. A heater cannot remain powered, and warmth is borrowed from another system. A memory chip fails, and its instructions are divided among surviving locations. The machine does not heal in a biological sense. It becomes a new configuration of its remaining parts. This flexibility was possible because the original design did not reduce every system to a single path. Redundant hardware, separable circuits, programmable computers, and carefully recorded interfaces left room for future engineers to make choices that the original team could not have predicted. Still, redundancy is not endless. Every workaround consumes something. A backup thruster accumulates wear. A memory region used for relocated code is no longer free for another purpose. A system switched off to save power may never awaken again. The number of possible configurations grows smaller with time. That is why the recovery of 2024 was not a return to youth. It was a deliberate extension of an old machine's useful life. The spacecraft resumed its work while carrying the physical evidence of the failure within it. Cosmic rays continue to pass through Voyager. Most leave no important trace. Some deposit charge in electronic material. A high-energy particle can alter a stored bit, disturb a circuit, or gradually damage the crystalline structure of a component. Error detection routines and careful design can protect against many such events, but no shielding can remove every risk across half a century. Voyager's computers were built to endure radiation, yet they were not built with the expectation of operating indefinitely beyond the heliosphere. Their continued function depends on both robustness and restraint. They perform a narrow set of tasks. They do not waste energy on displays, rapid calculations, or layers of software unrelated to the mission. They receive commands, monitor the spacecraft, prepare data, and help maintain the link home. The simplicity is part of their strength. So is the community that still understands them. Some of the people who now care for Voyager were children when it passed Saturn. Others had not yet entered the world. They inherited a conversation already in progress, along with the responsibility to preserve the language spoken at its distant end. Across generations, engineers have carried that language forward. The code inside Voyager remains small enough to fit many times within a single photograph taken by a modern phone. Its reach, however, extends farther than any other active computer created by human hands. It does not need to be fast. It needs to remember what to do, one instruction after another, while its signal crosses the distance home. The reward for keeping Voyager alive is not found in the machinery alone. It is found in the place the machinery has reached. The sun surrounds itself with more than light. From its upper atmosphere, charged particles stream outward in every direction. Electrons and atomic nuclei move through the solar system as the solar wind, carrying part of the sun's magnetic field with them. Near Earth, this flow passes our planet at hundreds of kilometers per second. It continues beyond Mars, Jupiter, Saturn, and Neptune. Long after sunlight has become faint, the solar wind still presses outward against the material between the stars. The result is the heliosphere. It is an immense region shaped by the sun's particles and magnetic influence, a moving enclosure carried through the local galaxy. As the solar system travels around the Milky Way, the planets orbit within it. Comets pass through it. Earth and everything that has lived here have spent their entire history inside its changing protection. The heliosphere is not a solid shell. It has no surface that could be photographed like the edge of a planet. Its boundaries are formed by interacting particles, magnetic fields, and pressure. The solar wind pushes outward. The interstellar medium pushes back. Between them lies a broad and active transition. Voyager 1 began to enter that transition long before it reached interstellar space. In December of 2004, at about 94 times Earth's distance from the Sun, the spacecraft crossed the termination shock. Until that point, the solar wind had been moving faster than waves could travel through its plasma. At the shock, the flow slowed abruptly from supersonic to subsonic speed. The particles did not stop. They compressed, heated, and changed direction as they entered a region called the heliosheath. Here, the outward wind encountered increasing resistance from the surrounding galaxy. Models had predicted such a region, but a mathematical boundary is different from a spacecraft passing through it. Voyager found a place more uneven than the simplest pictures suggested. Particle intensities rose and fell. Magnetic structures shifted. The outward speed of the solar wind declined until its radial motion became difficult to detect. Instead of ending in one clean step, the sun's domain faded through years of changing conditions. The spacecraft spent nearly 8 years in this outer layer. During that time, its instruments watched two populations of particles move in opposite directions. Particles associated with the sun became less common. High-energy cosmic rays arriving from beyond the heliosphere became more abundant. Cosmic rays are not beams of visible light. They are atomic nuclei and other particles moving through the galaxy at tremendous energies. Some are accelerated by the shock waves of supernova remnants and by other powerful astrophysical processes. Inside the heliosphere, the solar wind and its embedded magnetic field deflect and slow part of this incoming population. The sun creates a measure of shielding. It does not stop every cosmic ray, but the environment within its influence differs from the space outside. As Voyager moved through the heliosheath, the rising number of galactic particles suggested that the shield was thinning. Then, in August of 2012, the pattern changed sharply. Particles from the heliosphere dropped. Galactic cosmic rays increased. Voyager had crossed the heliopause, the boundary where the solar wind no longer dominated the surrounding plasma. The crossing occurred at roughly 122 astronomical units from the Sun. That distance is immense by planetary standards, yet it is only a beginning when compared with the full reach of objects gravitationally connected to the Sun. The distant Oort cloud may extend thousands or tens of thousands of astronomical units outward. Voyager entered interstellar space, but it did not leave every possible definition of the solar system behind. Interstellar space in this context means the region beyond the heliopause, where the local environment is governed more by the material between stars than by the solar wind. The spacecraft remains under the Sun's gravity and could continue passing through distant solar territory for ages. At first, the mission team could not declare the crossing with complete confidence. One expected sign was missing. Scientists thought the magnetic field might rotate noticeably as Voyager passed from the Sun's field into the interstellar magnetic field. The measured direction changed far less than anticipated. This did not mean the spacecraft had remained inside. It meant the boundary and the magnetic fields around it were arranged differently from some models. The interstellar field may be bent around the heliosphere, following its outer shape rather than meeting it at a simple angle. There was another difficulty. Voyager 1's plasma science instrument had stopped providing useful measurements shortly after the Saturn encounter. That instrument would have offered the most direct way to determine the density, temperature, and motion of the surrounding charged particles. The spacecraft needed another method. Its plasma wave subsystem could detect oscillations in the local electron population. When a strong disturbance from the Sun traveled outward and reached the space around Voyager, it caused the plasma there to vibrate at frequency related to its electron density. The instrument detected those vibrations. They were not sound waves moving through ordinary air. Interstellar space is far too thin for that familiar kind of sound. They were electrical oscillations in ionized gas, recorded by antennas and converted into data that could be represented at audible frequencies on Earth. From those frequencies, scientists calculated the density of the plasma surrounding the spacecraft. It was far greater than the thin plasma measured in the outer heliosphere and consistent with the local interstellar medium. Earlier data revealed a weaker event from late 2012. By comparing the observations, the team concluded that Voyager had crossed the heliopause on August 25th of that year. The boundary became known after the spacecraft had already passed it. This is often how exploration works. The traveler crosses a place before those watching from a distance fully understand what the measurements mean. Only later do separate clues form a coherent picture. Beyond the heliopause, Voyager entered the very local interstellar medium. This region is not empty. It contains hydrogen, helium, electrons, dust grains, cosmic rays, and magnetic field. Its matter is sparse beyond ordinary experience, yet, over astronomical distances, it shaped stars, clouds, radiation, and the boundaries of stellar systems. The plasma wave instrument has continued measuring changes in electron density. Some signals arrive when disturbances created by solar activity travel far beyond the heliosphere. A major eruption near the Sun can send a pressure wave outward, crossing the planets and reaching Voyager many months later. There, the disturbance makes the surrounding plasma oscillate strongly enough for the spacecraft to detect it. The Sun can no longer fill Voyager's environment with solar wind, but it can still touch that environment with passing waves. Between those stronger events, scientists have also identified a faint, persistent plasma signal. Its changing frequency provides a more continuous view of the density around the spacecraft. Rather than revealing a uniform medium, the observations show fluctuations and structure. The space between stars has texture. There are regions of slightly different density, pressure fronts, shocks, and magnetic changes. Voyager moves through only one narrow path, but no telescope near Earth can replace that local measurement. Its magnetometer supplies the second surviving view. Mounted far from the spacecraft body on a long boom, the instrument measures the strength and direction of the surrounding magnetic field. It follows variations too subtle for human senses and too distant for direct sampling by any other active mission. Together, the two instruments describe a medium that cannot be photographed. One listens to the electrical behavior of plasma. The other follows an invisible field threading through it. Their data reveal the environment not as an image, but as a changing sequence of frequencies, directions, and strengths. You are resting deep within the Sun's enclosure now. Around Earth, the solar wind continues its outward passage. It moves beyond the orbit of every planet and presses into the interstellar material Voyager has reached. The boundary is unimaginably distant, yet the same star that warms the ground beneath us also shapes that faraway frontier. Voyager carries our measurement across it. Each surviving data packet tells us something no remote observation can provide in quite the same way. It shows how dense the nearby plasma is, how the magnetic field bends, and how disturbances move through the local interstellar medium. The spacecraft's remaining warmth, therefore, supports more than aging electronics. It maintains a scientific outpost on the far side of the Sun's protective boundary. As long as the plasma wave instrument can listen, the magnetometer can measure, and the antenna can return their results, a thin line of knowledge remains open between Earth and the space between stars. Voyager survives so that this distant region does not have to remain entirely unseen. The spacecraft's last years are not defined by a single approaching failure. They are shaped by many small limits moving toward one another. Electrical power declines each year. Thruster passages narrow. Computer memory carries the history of repaired faults. Heaters operate closer to their minimum margins. The radio link weakens as distance grows. Any one of these systems may continue for a while longer, but the mission depends on all of them overlapping at the same time. That overlap is becoming smaller. Voyager's radioisotope generators lose several watts of electrical output each year. The decline is gradual enough to measure and plan for, yet relentless enough that every operating season brings another decision. A system kept active today may require something else to be retired tomorrow. Mission planners do not simply rank instruments from most important to least important. They ask how each instrument supports the science still possible at Voyager's location. They examine how much electricity it consumes, how much internal heat disappears when it is switched off it, and whether turning it off changes the temperature of nearby equipment. They consider whether the instrument can ever be restarted. They also examine how the spacecraft's computers, transmitter, attitude control, and fault protection will respond to the new power balance. A single command can change several parts of the spacecraft at once. This is why the end of a long mission arrives through preparation rather than surprise. For years, engineers have rehearsed the future in thermal models and power tables. They estimate the output of the generators, the needs of the radio, and the point at which another scientific load can no longer be supported. The dates remain uncertain because aging hardware does not always follow prediction precisely. Some components tolerate colder conditions than expected. Others develop problems no model could foresee. The broad direction, however, is fixed. There will be less power next year than there is now. That fact has already changed the spacecraft from a many-instrument observatory into a smaller and more specialized presence. The cameras ended their work long ago. Spectrometers and planetary instruments followed. Particle detectors that once helped identify the heliopause have reached the end of their operations. What remains is selected for the region Voyager now occupies, and for the energy that can still be supplied. The magnetometer and plasma wave system continue because they can describe the interstellar medium in ways no other operating spacecraft can. They are also different instruments with different needs. The magnetometer senses a field without needing to expose a camera or move a mechanism. The plasma wave system listens through long antennas for electrical oscillations in the surrounding charged particles. Their measurements can be modest in volume, which suits the narrow radio link. Neither requires a nearby planet or a bright source of reflected light. Keeping them active still costs more than the instruments alone consume. Their data must pass through computers. The spacecraft must remain oriented. The transmitter must operate. Selected electronics must stay warm enough to process and send the results. The Deep Space Network must dedicate time to receiving them. Science at Voyager's distance is therefore a whole system activity. There is no separate boundary between an instrument reading and the engineering that makes the reading possible. A magnetic field measurement depends on a thruster firing correctly days earlier. A plasma observation depends on a heater preserving a circuit months before that. A line in a scientific paper may trace back to a power decision made by someone studying a thermal diagram in California. The people making those decisions belong to several generations. Some worked on Voyager before launch. They knew the spacecraft as drawings, components, test articles, and assembly procedures. Others joined after the planetary encounters, when the mission had already become something different from its original plan. Still, others arrived after Voyager crossed into interstellar space and learned the vehicle through documents, archived commands, and the experience of older colleagues. The mission has lasted long enough for knowledge transfer to become part of the spacecraft's survival system. A memory map preserved in an archive can matter as much as a backup circuit. A handwritten note about a switch may explain behavior seen 40 years later. A retired engineer's recollection can help a younger team understand why a line in the software was written in an unusual way. The machine travels alone, but the knowledge required to operate it does not. It moves through people. One generation builds a system with margin. Another learns how that margin behaves in flight. A later one discovers which assumptions were correct, which were too cautious, and which hidden pathways can still be used when a component fails. That continuity is not automatic. Old programming languages must remain readable. Obsolete hardware descriptions must be preserved. Engineers must resist the temptation to simplify records that may contain details whose importance will only become clear decade. Institutions must make room for long missions, even when newer spacecraft compete for attention and funding. Voyager's longevity is often described as a triumph of construction, and it is, but it is equally a triumph of remembering. Without memory on Earth, the memory aboard the spacecraft would be far less useful. Every command sent now carries the work of people who are no longer in the control room. The shape of the antenna, the arrangement of the fuel lines, the choice of plutonium, the location of each software routine, and the behavior of each backup system were decided by teams working in another century. Their decisions continue to unfold at the edge of the sun's influence. The present team adds its own layer. A heater sequence tested today may preserve a thruster for the next group of engineers. A repaired memory path may keep telemetry available long enough for another anomaly to be understood. A carefully documented workaround may become the starting point for a decision years from now. No one can restore the power already lost. What they can preserve is the usefulness of what remains. That distinction gives the final years their character. The goal is no longer expansion. Voyager will not gain a new camera or a stronger transmitter. It will not turn toward another planet. The work is to keep a narrow scientific purpose intact, while the surrounding machine gradually becomes simpler. There is dignity in that kind of engineering. It accepts limits without surrendering early. It does not confuse caution with passivity. It knows that a system can be fragile and still be worth operating, provided the risks are understood and the remaining value is real. The mission will eventually reach a point when the numbers no longer balance. Perhaps an instrument will be turned off because the generators cannot support it. Perhaps the transmitter will become too costly to operate alongside attitude control. Perhaps a component will fail in a way that no remaining memory, heater, or redundant branch can bypass. The final command may not feel final when it is sent. It may be an ordinary attempt to conserve power, restore telemetry, or adjust the spacecraft's pointing. The last useful data may arrive without ceremony. Only later, after repeated listening and careful analysis, may the team understand that no further answer is coming. That moment will not erase the mission. The measurements already returned will remain. The engineering lessons will remain. The heliopause crossing, the interstellar plasma record, the magnetic field observations, and the planetary discoveries will continue to shape research. Long after the radio link ends, the silence will mark the end of contact, not the end of motion. Voyager will continue on the path established by its encounters with Jupiter and Saturn. Its generators will keep releasing heat, though no working system may be left to use it. Its body will cool. Its dish may drift away from the computer code that once organized a signal will remain stored in aging material until radiation and time gradually alter it beyond recovery. Before that future arrives, the spacecraft is still part of the present. A signal can still be scheduled, a command can still be prepared, a measurement can still cross the distance and enter the human record. For now, the chain remains unbroken, carried forward by a machine growing colder, and by people who continue to remember how to listen. When the final signal leaves Voyager 1, the spacecraft may not know that anything has changed. Its remaining circuits will continue according to their programming. The radioisotope generators will keep releasing heat. The antenna may hold its direction for a while. A sensor may still register a magnetic field or a passing disturbance in the interstellar plasma. What ends first will be the connection. On Earth, antennas will turn toward the place where Voyager should be. Receivers will search the expected frequencies. Engineers will account for motion, for timing, and the possibility of a weakened or distorted signal. They will listen through the radio noise and repeat the effort, because a spacecraft this old has returned before from conditions that once appeared final. There may be no clear boundary between the last difficult contact and the first permanent silence. A packet may arrive incomplete. A carrier may appear without readable data. Days may pass between attempts. The team may send commands designed to restore pointing, change a transmitter mode, or protect the remaining power system. Each command will travel outward through the same long interval. By the time it reaches Voyager, Earth will have moved farther along its orbit. The people waiting for the response will have slept and awakened. Clouds will have crossed continents. The planet will have turned beneath the radio antennas that continue to follow one distant direction in the sky. Then, another interval will pass. The answer may come, or it may not. If it does not, the spacecraft will still be there. Silence does not remove an object from space. It only removes our immediate knowledge of its condition. Voyager will continue moving under the momentum given to it by its launch and by the gravitational encounters that shaped its path. Jupiter changed its speed. Saturn changed its direction. The close passage by Titan placed it on a route rising away from the broad plain in which most planets travel. That choice ended the possibility of another planetary encounter, but it opened the path. Voyager follows now. The spacecraft will not stop when its transmitter stops. There is almost nothing around it to create drag. The interstellar gas is too thin to slow it meaningfully on human timescales. Dust grains may strike its surfaces from time to time, leaving marks too small for anyone to inspect. Cosmic rays will continue passing through its structure, changing atoms and electronic materials long after the electronics cease to function. Its temperature will gradually fall. Without active systems converting electricity into heat, the interior will lose warmth through radiation. The remaining plutonium will continue to decay, but the available heat will diminish over centuries. The reflective blankets will still delay the loss, though there will no longer be a mission team measuring the result. The spacecraft will become colder, simpler, and harder to distinguish from the space around it. Its shape will remain recognizably artificial. The high-gain antenna will still curve around the point where radio waves were once focused. The long magnetometer boom will remain extended from the body. The 3 radioisotope generators will stay fixed to their supporting structure. Beneath protective coverings, equipment boxes will preserve the arrangement of a machine designed for a journey that exceeded every planned boundary. The golden record will remain attached to its side. Its grooves contain sounds and images selected to describe Earth to an unknown finder. Wind, water, voices, animals, music, diagrams, and greetings were placed together on a physical object expected to outlast the electronics carrying it. The record was never a realistic attempt at rapid communication. Space is too large, and Voyager's path is unlikely to bring it close to another inhabited world. The chance that someone will discover it is small, beyond meaningful calculation. Its value does not depend on being found. The record is evidence that, for a brief period, people on one planet considered what they would say beyond their own time. They chose the sound of a heartbeat. They chose waves reaching a shore. They chose human voices speaking across differences that seemed large on Earth and very small when placed together on a spacecraft leaving the Sun. For as long as Voyager remains intact, those choices travel with it. In about 40,000 years, the spacecraft will pass within roughly 1.5 light-years of the red dwarf Gliese 445. By then, the star itself will be closer to the Sun than it is today, because both are moving through the galaxy. Voyager will not enter orbit around it. The passage will occur across a distance still much larger than the space between the suns and its nearest stellar neighbor. There may be no planets nearby and no observer to notice the crossing. The spacecraft will continue beyond, following a path altered very gradually by the gravitational field of the galaxy and by distant stars. 40,000 years is longer than recorded human history. For Voyager, it is only the beginning of the silent voyage. The Sun will continue changing behind it. Over billions of years, the hydrogen in the solar core will diminish. The star will grow brighter, expand, and eventually leave its present state. Earth will be transformed long before Voyager completes even a small fraction of its journey around the Milky Way. The spacecraft will not witness these changes. Witnessing belongs to living minds and working instruments. Voyager will simply occupy a sequence of positions, moving through regions of gas, magnetic field, and starlight. That continued motion carries no message back to us. Yet knowing it will happen changes the way the mission can be understood. Voyager was never only a machine sent to Jupiter and Saturn. It became a measure of distance, duration, and care. It showed that a device built for a few years could remain useful across generations. It revealed that engineering can continue after the original plan has ended, provided enough knowledge, restraint, and attention remain. Its long life was never endless. No machine needs to last forever to have completed its purpose. Voyager returned close views of worlds that had existed for billions of years beyond the reach of human sight. It found active volcanoes on Io and complexity within Saturn's rings. It helped turn distant moons into physical places with weather, geology, ice, and hidden interiors. Later, it carried instruments across the heliopause. It measured the region where the solar wind gives way to the interstellar medium. It allowed us to sample the plasma and magnetic field beyond the Sun's enclosure, the Sunsin, while remaining connected to the planet where the spacecraft began. That connection was always temporary. Radio waves crossed the distance only because power remained. Antennas aligned, receivers listened, and people continued the work. The mission survived through a series of finite things, arranged with unusual care. A limited amount of plutonium, a limited supply of hydrazine, a limited number of working circuits, a limited span of human attention. Together, they created nearly half a century of communication, with a machine moving away from everything familiar. The end will not diminish that achievement. When the signal is gone, the measurements will remain in archives and scientific papers. The lessons will remain in spacecraft designed by people who studied Voyager's successes and failures. The knowledge will continue through missions that travel toward the outer heliosphere with different instruments and different questions. For a time, no spacecraft may replace its position. The interstellar medium will continue changing without a human instrument nearby to record it. Solar disturbances will move beyond the heliopause and pass through plasma, no longer monitored by Voyager. The magnetic field will bend and fluctuate without becoming numbers on an Earth-bound screen. That absence may make the old data more valuable. Each surviving observation will represent a moment that cannot be repeated, a measurement taken along one narrow path through a region no other instrument occupied at the same time. Tonight, Voyager is not yet only a memory. It is still moving, still carrying warmth from radioactive decay, and still holding the possibility of another signal. Far behind it, Earth continues beneath the Sun, small enough to vanish within the beam of its antenna, and important enough to remain the direction that antenna seeks. The distance grows, the power fades, and the little spacecraft keeps its face turned home.